Welcome to part 2 of our navigation camera series, camera types. In the previous video, we explored the key specifications that define camera performance, including resolution, field of view, focal length, sensor size, and pixel size. Now we will look at the different types of cameras used in unmanned ground vehicles, including day cameras, low-light cameras, infrared cameras, thermal cameras, and perception cameras. We will understand how each camera works, where it is used, and how multiple camera types combine to support navigation, observation, and autonomy.
Welcome to part 2 of our camera series, Types of Cameras. Before we study specific camera technologies, it is important to understand that cameras can also be grouped by the function they perform on an unmanned ground vehicle. First, we have navigation cameras that help the operator drive safely by providing front, rear, and side views with wide coverage and low latency. Next, we have observation cameras are used for surveillance, reconnaissance, and target identification. These usually offer higher resolution, optical zoom, thermal imaging, and stabilized movement. And lastly, we have perception cameras that support autonomy. They help the vehicle detect obstacles, measure distance, classify terrain, recognize objects, and plan a safe path. The key idea is simple. Navigation, observation, and perception cameras perform different roles, but they work together to create a complete visual system for an unmanned ground vehicle.
In this video, we will explore 5 important categories of cameras used in modern unmanned ground vehicles. We will begin with day or RGB cameras, which provide natural color images for navigation and observation. Next, we will look at low-light and infrared cameras, which improve visibility in darkness and poorly illuminated environments. We will then study thermal cameras, which detect heat signatures and support operation in complete darkness, smoke, and challenging weather conditions. After that, we will cover stereo and depth cameras, which help measure distance and detect obstacles. Finally, we will introduce event and multi-spectral cameras, which support high-speed sensing, advanced perception, and specialized mission applications. Together, these camera types form a complete visual sensing system for a UGV. Let's start the session by understanding day or RGB cameras. Let us begin with day or RGB cameras. These cameras capture visible light and create natural color images using red, green, and blue channels. Because the output is similar to human vision, RGB cameras are the most familiar and widely used cameras on unmanned ground vehicles. They are commonly installed at the front, rear, and sides of the vehicle to support navigation, teleoperation, and obstacle awareness. Higher resolution RGB cameras may also be mounted on a mast for surveillance, reconnaissance, and target observation. In addition, RGB video can be processed by AI systems for object detection, terrain classification, and visual tracking. In simple terms, RGB cameras provide the color, detail, and visual context needed for daytime unmanned ground vehicle operation.
Day, or RGB cameras, offer several important advantages for unmanned ground vehicles. They provide natural color images that are easy for operators to understand. They also capture useful visual details such as road markings, terrain features, uniforms, vehicles, and equipment. RGB cameras are widely available, cost-effective, and well-suited for AI-based object detection and visual tracking. However, they also have limitations. Their performance drops significantly in low-light conditions, and they cannot operate effectively in complete darkness without additional illumination. They may also be affected by glare, deep shadows, smoke, dust, fog, and harsh weather. Most importantly, RGB cameras cannot detect heat signatures. For this reason, they are often combined with low-light, infrared, or thermal cameras for reliable day and night UGV operation. This image shows how an RGB camera supports navigation and scene understanding. On the left, we see the natural camera view captured in full color. It shows the road, lane markings, traffic signal, road signs, vehicles, and pedestrian areas, just as an operator would see them. In the center, the RGB camera feed is processed using image processing and AI perception algorithms. On the right, the same scene is converted into a highlighted navigation view. Lane markings are traced, traffic signals and road signs are identified, vehicles are detected as obstacles, and the zebra crossing is clearly marked. The key point is that an RGB camera does more than provide video. When combined with AI, it helps the vehicle understand the road and navigate more safely.
Let's take a quick look at our agenda. We have now completed our introduction to day or RGB cameras and understood how they support color imaging, navigation, and observation. Let us now move to the next topic, low light and infrared cameras. These cameras help a UGV operate when visible light is limited, especially during dusk, nighttime, and poorly illuminated missions. Low-light cameras are designed to produce usable images when very little visible light is available. Unlike a standard day or RGB camera, which performs best in normal daylight, a low-light camera uses a more sensitive sensor and image processing to capture and enhance weak light from the scene. In moderate low light, it may still produce a color image. As conditions become darker, the output may shift to reduced color or black and white for better visibility. These cameras are useful during dusk, dawn, moonlight, inside tunnels, warehouses, shaded areas, and other dim environments. However, they still need some available light. In complete darkness, they normally require infrared illumination or support from a thermal camera. For Yeezy's low-light cameras provide a familiar visual view for safer night navigation and observation. An IR camera or infrared camera is designed to create images using near-infrared light, which is invisible to the human eye. The camera usually works together with an IR illuminator. This illuminator projects invisible infrared light onto the road, terrain, or nearby objects. The reflected light is then captured by the IR-sensitive camera sensor and converted into a clear, usually black and white image. This makes IR cameras useful for night driving, tunnel navigation, obstacle detection, and short-range surveillance. The key difference between an IR camera and a low-light camera is the source of illumination. A low-light camera uses and amplifies the small amount of ambient light already available. An IR camera actively illuminates the scene using infrared LEDs. Therefore, a low-light camera may retain color, but it needs some visible light. An IR camera usually produces monochrome video, but it can work in complete darkness within the range of its illuminator. For reliable UGV night operation, both technologies can be used together.
This image compares the same front camera view from an unmanned ground vehicle using 3 different cameras, namely day, low light, and IR camera. On the left, the day or RGB camera view provides a clear natural color image with good detail of the road, vegetation, obstacles, and surrounding structures. In the center, the low-light camera shows the same scene in dim conditions. The image is darker and the colors are reduced, but important terrain and obstacle details are still visible using the available ambient light. On the right, the IR camera produces a monochrome night vision image. It uses infrared illumination to reveal the road, rocks, vegetation, and nearby objects even in darkness. The key point is simple. Day cameras provide color, low-light cameras enhance limited light, and IR cameras provide visibility when normal light is no longer sufficient.
While IR cameras are useful for night navigation, the military may have concerns about using them continuously in tactical environments. The main issue is the IR illuminator. Although its light is invisible to the naked eye, it can be detected by enemy night vision goggles, IR-sensitive cameras, and other electro-optical sensors. The main military concerns are first, that the illuminator may reveal the presence of the unmanned ground vehicle. Second, it may expose the vehicle's approximate position and direction of movement. Third, the IR beam can indicate where the camera is looking, reducing the advantage of covert surveillance. For this reason, the military may prefer passive sensors such as low light or thermal cameras, while using active IR illumination only when necessary and under operator control. Let's take a quick look at our agenda. We have now completed low light and infrared cameras and understood how they improve visibility in dark or poorly illuminated environments. Let us now move to thermal cameras. Unlike conventional cameras, thermal cameras detect heat emitted by objects, making them highly effective for night operations, surveillance, and target detection.
A thermal camera creates an image by detecting infrared energy emitted by objects because of their temperature. Unlike a day, low light, or IR assisted camera, it does not depend on visible light or an external illuminator. Thermal energy from the scene first enters through the thermal lens. The detector then measures small differences in infrared radiation across the image. The camera's processor converts these temperature differences into a visible thermal picture. Warmer and cooler areas are shown using brightness levels or artificial color palettes such as white hot, black hot, or color mode. So instead of showing the natural color of an object, a thermal camera shows its heat pattern. This allows people, vehicles, engines, and other warm objects to remain visible even in complete darkness. This image shows how a UGV thermal camera sees the environment at night. The scene is displayed in a thermal view, where warmer objects appear much brighter than the cooler background terrain. Here, we can clearly identify three important targets. First, a person standing on the road. Second, another vehicle farther ahead. And third, an animal on the side of the path. Even though the surroundings are dark, the thermal camera makes these objects visible by detecting the heat they emit. This is the main strength of thermal imaging. It helps the UGV detect people, vehicles, and animals in complete darkness, even when a normal day camera or low-light camera may struggle to provide a clear image. This image compares the two main types of thermal cameras used in automotive or unmanned ground vehicle applications, LWIR and MWIR. LWIR stands for long-wave infrared and typically operates in the 8 to 12 micrometer range. These cameras usually use uncooled microbolometer detectors, making them compact, lower in power consumption, and easier to integrate. They are well suited for front thermal navigation, short to medium range surveillance, and general situational awareness. MWIR stands for mid-wave infrared and typically operates in the 3 to 5 micrometer range. These cameras often use cooled detectors, which provide higher sensitivity and better long-range performance. However, MWIR systems are larger, more complex, more expensive, and consume more power. In simple terms, LWIR is the practical choice for most unmanned ground vehicle navigation needs, while MWIR is preferred for long-range surveillance and target detection. Thermal cameras are extremely useful for night detection, but they also have important limitations. The first example shows rain. Heavy rain absorbs and scatters infrared energy, reducing image clarity and detection range. The second example shows glass. Thermal cameras generally cannot see through normal glass because the glass blocks long-wave infrared radiation. Instead, the camera mainly sees the temperature of the glass surface. The third example shows objects at similar temperatures. When a person, vehicle, or obstacle is close to the temperature of the background, thermal contrast becomes low and the target may blend into the scene. The final example shows fog. Although thermal cameras may perform better than visible cameras in some conditions, dense fog can still reduce contrast and range. So thermal cameras are powerful, but they should be combined with RGB or low-light cameras for reliable all-condition unmanned ground vehicle operation. This table compares leading thermal camera manufacturers and models suitable for automotive and unmanned ground vehicle applications. It covers solutions from Teledyne FLIR, Leonardo DRS, and Sierra Olympia Technologies, with resolutions ranging from 320 by 256 to full high-definition thermal imaging. The comparison also highlights thermal technology, pixel pitch, and integration interfaces such as GMSL, FPD-Link, USB, HDMI, and IP video, helping engineers shortlist the right camera for navigation, surveillance, and autonomous perception.
Let's revisit our agenda. We have now completed thermal cameras and understood how they detect heat signatures for night operations, surveillance, and target detection. Let us now move to stereo and depth cameras. These cameras help the UGV measure distance, understand its surroundings, and detect obstacles for safer navigation and autonomous operation. A stereo camera uses two synchronized cameras placed a fixed distance apart, similar to human eyes. Each camera captures the same scene from a slightly different position. The system then compares the left and right images and measures the difference, known as disparity. Nearby objects show a larger disparity, while distant objects show a smaller one. Using this information, the camera calculates depth and creates a three-dimensional understanding of the environment. For an unmanned ground vehicle, this helps with obstacle detection, distance measurement, terrain mapping, trench detection, and autonomous path planning. Unlike a normal RGB camera, which provides only a two-dimensional image, a stereo camera adds depth information, helping the vehicle understand not only what is ahead, but also how far away it is. Here we see how a stereo camera creates depth information. First, the stereo camera uses two synchronized cameras placed side by side. Both capture the same scene at exactly the same time. Second, because each camera views the scene from a slightly different position, the left and right images are not identical. Third, the system compares these two images, measures the difference, called disparity, and uses it to calculate depth. That is how a stereo camera estimates how far objects are from the vehicle. In this image, we see the different types of information produced by a stereo camera. First, it provides the left and right visual images, which show the scene in normal color and detail. Second, it creates a depth map, where each pixel carries a distance value, helping the system understand which objects are near and which are far. Third, it can generate a point cloud. A point cloud is a three-dimensional set of points in space, where each point represents the position of part of an object or the environment. In simple terms, it is a 3D digital shape of the scene. Finally, the system can identify objects and estimate their distance for safer navigation. A point cloud is made up of thousands of individual points, and each point contains three coordinates, x, y, and z. In this example, x represents the point's lateral position, or how far it is to the left or right. Y represents its height, and z represents the forward distance from the camera. To calculate the straight line distance from the camera to that point, we use the formula. D equals the square root of x squared plus y squared plus z squared. For example, if x is 1 meter, y is 0.5 meters, and z is 6 meters, the total distance is approximately 6.1 meters. This allows us to measure the position of objects in three-dimensional space.
This image explains how an unmanned ground vehicle estimates the distance to an object in front of it using a point cloud. A detected object is not represented by just one point. It is represented by a cluster of many 3D points. From this cluster, the system can calculate several useful values. First, it can find the closest point on the object. This is the nearest reliable point to the unmanned ground vehicle and is the most important value for collision avoidance and emergency stopping. Second, it can calculate the average distance of all object points, which gives a more stable estimate of the object's overall range. Third, it can find the center or centroid of the object. This is useful for tracking and representing the object's position. Finally, the system can estimate the object's width, height, and depth, which helps understand the object's size and shape. In practice, the most commonly used safety metric is the nearest reliable point, while centroid and object size are widely used for tracking, classification, and path planning. This image explains how depth cameras help an unmanned ground vehicle navigate safely. First, the system identifies the ground plane and separates drivable terrain from objects above or below it. It then detects obstacles such as rocks, walls, people, and vehicles. Next, the depth information is converted into an occupancy grid, marking areas as free, occupied, or unknown. The camera also analyzes terrain features such as slopes, rough ground, steps, and trench edges. Using this information, the UGV calculates a safe path around hazards. The complete process is depth sensing, terrain understanding, mapping, and path planning. Apart from stereo cameras, there are two other types of depth cameras: time of flight or TOF cameras and structured light cameras. Time of flight and structured light cameras are two active depth sensing technologies used to measure the three-dimensional shape of a scene. A time of flight camera emits infrared light and measures how long or by how much its phase changes before the reflected signal returns. It uses this information to calculate distance and generate a real-time depth map. This makes it useful for obstacle detection, indoor navigation, and docking. A structured light camera works differently. It projects a known infrared pattern of dots or lines onto an object. The camera observes how the pattern bends or deforms and uses that change to calculate depth. Structured light is best for detailed, close-range tasks such as object localization and robotic manipulation. Both technologies work in darkness, but because they actively emit infrared energy, they may be detectable and can be affected by sunlight or interference. Because time of flight and structured light cameras actively emit infrared energy, they may be detectable by enemy night vision or IR-sensitive sensors. This makes them less suitable for military operations.
Let's take one last look at our agenda. We have now completed stereo and depth cameras and understood how they help a UGV measure distance, detect obstacles, and interpret its surroundings. Let us now move to the final topic: event and multispectral cameras. These advanced cameras support high-speed sensing, specialized detection, and more intelligent perception in complex mission environments. An event camera works very differently from a normal camera. A normal RGB camera captures complete images at fixed frame rates, such as 30 frames per second. An event camera does not continuously record full frames. Instead, each pixel independently detects a change in brightness. Whenever a pixel becomes brighter or darker, it generates an event. That event records the pixel's X and Y position, a precise timestamp, and the direction of brightness change, called polarity. So an event camera reports only what is changing in the scene, making it extremely fast and efficient for motion detection. This image shows how an event camera observes the scene. Instead of recording every part of the image continuously, it responds only where brightness changes occur. In this example, the moving person and the moving UGV generate red and blue events around their edges. The stationary road, rocks, and background produce very few events because they are not changing. Each pixel works independently and reports the exact location and time of the brightness change. This asynchronous operation allows the camera to detect motion with extremely low latency. Let us see how an event camera can support an unmanned ground vehicle. Unlike a normal RGB camera, an event camera does not capture complete frames. It reports only brightness changes, giving very low latency, minimal motion blur, and strong performance during fast movement or sudden lighting changes. Each event contains the pixel position, an accurate timestamp, and whether brightness increased or decreased. For a UGV, this can support rapid obstacle detection, visual odometry, high-speed navigation, motion analysis, and target tracking. The limitations are that stationary objects generate little information, the output is not intuitive for operators, and specialized algorithms are required. Event cameras are being explored and deployed in defense applications, including drone detection, tracking, and other high-speed sensing tasks. For unmanned ground vehicles, they are best used alongside RGB, thermal, or other sensors rather than as the main driving camera. A multispectral camera captures images in several separate wavelength bands rather than only the red, green, and blue channels used by a normal RGB camera. These bands may include visible light, near-infrared, red edge, and shortwave infrared. Because different materials reflect energy differently at each wavelength, the camera can reveal information that is invisible to the human eye. It can also improve terrain analysis and object classification in haze, low light, or difficult environments. In simple terms, a multispectral camera does not just show how a scene looks, it helps the unmanned ground vehicle understand what the scene is made of. A multispectral camera supports several specialized applications. It can analyze vegetation and terrain, detect moisture or water, identify differences between soil, rocks, and man-made materials, and locate areas affected by fire or heat. It can also improve surveillance by detecting objects that blend into the visible background, including some forms of camouflage. In difficult conditions such as haze, smoke, or low contrast, additional spectral bands may reveal details that an RGB camera misses. This information helps the UGV improve terrain classification, target detection, autonomous navigation, and mission planning. Multispectral cameras offer several advantages over standard RGB cameras. An RGB camera captures only red, green, and blue visible light information. A multispectral camera captures additional wavelength bands, allowing it to detect moisture, distinguish materials, assess vegetation, and reveal features that may be hidden by haze or camouflage. However, this capability comes at a cost. Multispectral cameras are significantly more expensive, generate larger data volumes, and require more calibration, processing power, and specialized algorithms. Their images may also be less intuitive for a human operator than a normal color view. For UGV operations, their value lies in advanced terrain classification, material identification, environmental assessment, and target detection. They are therefore best used as specialized perception sensors alongside RGB, thermal, and depth cameras.
This brings us to the end of part 2 of our camera system series camera types. We explored day and RGB cameras, low light and infrared cameras, thermal cameras, stereo and depth cameras, and finally, event and multispectral cameras. Each camera type has its own strengths, and the right combination helps an unmanned ground vehicle operate more safely and effectively across different environments and mission conditions. Thank you for watching. I hope you found this session useful. Please continue to part 3, image formation, where we will understand how cameras capture and process an image. See you in the next video.